Let us now look how to optimize away the query phase of the write operations if we have synchronized clocks. So this was the last slide from our last unit. We said we can skip the query phase by using a timestamp for the write operation based on the current time of the local physical clock. And that's where we stand now. So let's look to clock synchronization. So we say that clocks Ci and Cj are delta synchronized if the following condition holds. What is the condition? For any time t, the absolute difference between the two clocks is bounded by delta. Then we say that these two clocks are synchronized. So we have bound on how two clocks drift apart. And saying that Ci and Cj are synchronized within 10 milliseconds means that delta is 10 milliseconds. That's an example. Now, we can say that a set of clocks are perfectly synchronized if for each pair of clocks they are zero synchronized. And that is clear because it means that they are exactly the same. Delta now goes to zero. So now we know what is a perfectly synchronized clocks. Quite often you see in many systems the notion of loosely synchronized clocks. These are many systems use loosely synchronized clocks. Loosely synchronized clocks attempt to be as close as possible to synchronized clocks, but they do not provide guarantee. This is very important. No guarantee is provided. So, which means that they can diverge arbitrarily. It's just, in the best cases, they are somehow synchronized. So in practice, they can arbitrarily be out of sync. So let us now look to the correctness of the write operation. We assume now, as a first trial, that our clocks are perfectly synchronized. So it's zero synchronized. In that case, actually, the registers satisfy linearizability. And let us see why. Assume that the first operation, O1, is a read or a write, and the second operation is a read. In this case, O1 will complete before O2 starts. And therefore, this read will read the timestamp of the latest write. So this is the same argument as before and nothing is changed. And therefore, of course, O1 is ordered before O2. Now let us look to this other case. O1 is a write operation and O2 is a write operation. And O1 is completed before O2 is evoked. In this case, the timestamp, which is the real clock of O1, will be less than the real clock of O2 when O2 is invoked. And that means that the timestamp of O1 is less than the timestamp of O2. And a value written by O1 is always overwritten by a value of O2 because O2 has a higher timestamp. Let us look at the case where O1 is a read and O2 is a write. This means there exists a write O0 that was invoked before O1, and the value returned by O1 is that of this previous write, O0. Which would mean then the timestamp of O1 is the same as the timestamp of O0. And of course, because the timestamp of O0 is less than the timestamp of O2, therefore the timestamp of O1 is less than the timestamp of O2. So here, if we have perfectly synchronized clock, we can order all operations and satisfy the linearizability condition. So what this means now? It means that we have, with the perfectly synchronized clocks, that writes and quite often also reads take one round trip and correctness is guaranteed. That is great. We have achieved very good performance for a linearizable read-write registers. Now let us look to the other case if the clocks were not perfectly synchronized. So if we have clocks that are loosely synchronized, then the algorithm that we just described does not satisfy linearizability. Why is that? Because write O1 will complete before write O2 is invoked. But of course the timestamp of O1 may still be greater than the timestamp by O2. And that will mean that O2 will be ordered before O1, and that of course violates linearizability. So important to remember in practice that many key value stores actually use the notion of loosely synchronized clocks. So for example, Cassandra uses loosely synchronized clocks in the way that I just mentioned. And therefore, in systems like that, we cannot guarantee linearizability. There are some other clocks that we just discussed before were in the previous course. We can use logical clocks to linearize all operation in logical time. If clocks are logical clocks, then we have shown in the previous course that shared memory does not satisfy linearizability. What this linearizability in logical time gave us, it gave us sequential consistency. And this has been discussed in the previous course. Now, are we happy now? The problem is solved. We can use perfectly synchronized clocks. And so everything is fine. Is that true? Of course, the answer is no, since perfectly synchronized clocks are impossible to implement. This is very important to emphasize. Perfectly synchronized clocks are impossible to implement. We have seen that physical clocks can drift apart from each other when we look to the clock rate and the possible drift. So any measurement of the clock time will contain some uncertainty. And synchronizing clocks across even an asynchronous network will add more uncertainty. We still can do something, and that we will introduce a new kind of clocks. The idea of this is, you've just seen it, which we call it delta synchronized, that clocks are somehow synchronized within a bound. So there is a maximum error bound on how the clocks can diverge from each other. And this we're going to call them interval clocks and discuss in the next unit.